Hello everyone, I'm Rohit, and in this video we will be discussing likelihood landscapes. This is a joint work with Fu, Prithvi, Daniel, and Judy. Convolutional neural networks are known to be vulnerable to adversarial examples. We start with an image of a giant panda. After adding a small, carefully crafted perturbation, we get an adversarial image of a giant panda misclassified as a hermit crab. This is an example of a possible threat to many real-world applications. Many works have proposed adversarial attacks to craft these adversarial examples. Some common attacks include FGSM, PGD, and Carlini and Wagner. There has also been work to make CNNs robust to these attacks. Popular directions include adversarial training, gradient regularization, and inference time input transformations. A natural question that arises here is, are there some inherent deficiencies in vanilla neural network training that attacks exploit or defenses counter? In this work, we explored this question by looking at how adversarial and clean samples fit into the marginal input distributions of trained models, log p of x. We first address how to compute the marginal log likelihood. Traditional CNN-based classifiers model the conditional distribution instead of the marginal distribution. To get around this, we leverage an energy-based model interpretation of discriminative classifiers. Classifiers typically consist of a feature extractor and a softmax layer. However, it turns out we can reinterpret the logics of a classifier to define a joint distribution of data points and labels. By marginalizing out y and taking the log, we can obtain the marginal log likelihood. Note that the normalizing constant z of theta involves integrating over the space of all images and in practice is intractable to compute. Thus, we focus on relative likelihoods instead, where we can cancel out the log z of theta term. Specifically, given a perturbed sample x prime and a clean sample x, we define the relative likelihood of x prime with respect to x as the difference between the two likelihoods. We visualize the relative likelihood values in the surrounding neighborhood of clean samples, and we coin the visualization as the relative likelihood landscape. The figure below shows that the relative likelihood landscape for a test sample under standard training. The center point shows the likelihood for the clean sample, while neighboring points show the values for perturbed samples. We see that with slight deviations, perturbed samples exist out of the high likelihood region. We then plot similar graphs for two popular defense techniques, Jacobian regularization and adversarial training. Both defenses intrinsically tend to flatten the likelihood landscapes. The stronger the defense, the more pronounced this effect becomes. Seeing this pattern, we design a way to quantify the flatness of likelihood landscape of a model by leveraging the approximate mass score. AMS quantifies how the marginal likelihood changes in the immediate neighborhood of a sample. We average a model's AMS near a test example to get a model-level flatness metric noted as phi flatness. In both cases of adversarial training and Jacobian regularization, we see that as we increase the strength of defense, both adversarial accuracy and flatness of likelihood landscape increase. This aligns with what we have seen in the previous qualitative analysis. We then ask if it is possible to improve adversarial robustness by directly regularizing models to induce a flat likelihood landscape. We explore this by regularizing the square of AMS alongside normal cross-entropy loss. Here are our experimental results on CFAR10. In terms of the flatness of likelihood landscapes, models trained with AMS regularization have flatter likelihood landscapes than Jacobian regularization and adversarial training, indicating that the regularization was successful. In terms of the adversarial accuracy, AMS regularized models have comparable adversarial robustness to that of Jacobian regularization. However, interestingly, both regularizations are still significantly more susceptible to adversarial attacks than adversarial training. To understand this, we conduct further analysis by looking at the flatness along the attack directions instead of random directions. Here, graphs show the likelihood landscapes projected using one FGSM direction and one random direction. Both Jacobian and AMS regularization are able to flatten out the random directions quite well. However, neither regularization is able to flatten in the FGSM direction as well as adversarial training. We suspect this is why AMS regularization does not have as high robust accuracy as adversarial training. We plan to explore a solution to flatten landscapes for the worst case directions soon. We hope you enjoyed our talk and we thank you for your time.